This is the half wave RL uncontrolled rectifier. Now here, in place of load, we are using the resistor and the inductor, and then it is connected in series with the power diode, and power diode is connected in series with the supply voltage. That supply voltage is AC. Your VS will be equal to the V peak times the sine wave, okay, sinusoidal omega t. Now here the waveform for the input voltage is given here. This is the input voltage. It is sinusoidal, and 0 to pi for the first positive half cycle, pi to 2 pi in the negative half cycle, again 2 pi to 3 pi in positive half cycle, and that signal repeats. So you'll have 4 pi and it goes on. Now here let's analyze the output voltage. Okay, output voltage across the load RL. Now from here it is easy to analyze using the Kirchhoff's voltage law. Now we are talking about the first positive half cycle, which means this one will be positive, and with respect to ground here it will be negative, which means your diode will be acting as a short circuit during this time, because the anode side is connected with the positive terminal of the supply voltage, and cathode is connected with the negative. So this diode will be act as a short circuit. Now here, if you apply the Kirchhoff's voltage law, it will be Vs minus the voltage drop across the diode, Vd minus the voltage drop across the load. Here across the load we can represent it with V output, and then it will be equal to 0. This is as per the Kirchhoff's voltage law, and we know that since your diode is like conducting, it is like a short circuit, so your this one will be equal to 0. Our output voltage will be equal to VO. Okay, so whatever the input voltage that we have, will be given to the output voltage. And then now let's again analyze with the current. Now since we have the inductor, the load inductor in this case, this inductor in the first positive half cycle, when the current is passing through this, it will try to store the energy. Okay, but again that current is not going to be like in the beginning. It's not going to be like, it's going to have the big magnitude, so the current is going to rise slowly. Okay, so our current, okay, this is same as output current, or we can also write it this one as input current. The shape of input current and output current will be same for this RL load. It will also same for that R load rectifier. So it is rising slowly. It's because of the nature of the inductor that we have. And somewhere like when it is at pi, it's supposed to be 0, but it's still rising. And then during that time, when it reach here, so we have the polarity reverse in the supply voltage. So this one will be negative and this one will be positive. So in the positive half cycle, our inductor was storing the charge. Okay, it was storing the energy in the form of magnetic field. So in the negative half cycle, when that the voltage, okay, supply voltage is passing like this, okay, this inductor will try to oppose. And again, if you look at the magnitude at the instant pi, your supply voltage or the input voltage is 0. And again, because of the sinusoidal in nature, it is increasing gradually. So during that time, the charge stored in the inductor will be more than the supply voltage. Here I am saying that at the instant, okay, when omega t is equal to at pi, your Vs will be equal to 0, or it will be minimum. So during that time your VL, okay, the voltage at the inductor will be greater than the Vs during this particular period of time. Or you can also say that during this period, okay, somewhere at this period your inductor voltage is more, which means inductor is still going to drive the current, okay, drive the current through the supply source and then through the diode until it finishes, or the charge stored in the inductor is equivalent or less than the input voltage. So during that time the current will be, okay, current that is driving from the input source and the current that's driving from the inductor will be, I mean, that resultant will be flowing through that one. So we will have something like this, okay. Somewhere, let's say at the angle beta, your current is going to become 0. That one is when that charge stored in the inductor is equivalent to or less than the magnitude which is driven by the input voltage. So here during that time we have seen that our inductor is still pushing the current. So in the output voltage also we can still expect that from the 0 it's still crossing somewhere like this, it's crossing like this. So at this angle, okay, now this will be near to that beta here, okay, somewhere at this beta. Now this magnitude, okay, this magnitude actually from here will be dependent on the value of your L. If your value L is bigger, then it may keep on conducting. So because of the nature or the depending upon the nature of the value of the inductor, we can have the continuous current waveform or the discontinuous current waveform. It will depend upon the value of the inductor. Now from here, so we can expect now our Vs from when omega t is equal to beta, our Vs will be now greater than the inductor voltage. So during that time this particular condition takes place, and then it will try to drive the current in the anti-clockwise direction. So during that time your diode will be in the reverse bias, okay, diode will be in the reverse bias and it will not conduct. So during that time your output voltage VO will be 0. Now this one we can also verify with the Kirchhoff's voltage law. Okay, I'm going to clear this one. Now when it is in the negative half cycle, that is when omega t is from pi to 2 pi, so you will have the circuit diagram as shown here, and this diode is reverse bias and it will act as a open circuit, so nothing is going to flow from here, which means you will have minus Vs. If you apply the KVL, it will be equal to minus Vs minus VO minus the voltage drop across the the voltage drop across the load, and voltage drop across the diode will be equal to 0. And then we know that since it's open circuit here, this one will be 0, so our VD will be equal to negative of Vs. So which means at this point, okay, from the, it's not pi, okay, sorry, here this is from beta, so from beta to 2 pi our output voltage across the diode will be minus Vs. So whatever the from here, from the beta, so our output voltage across the diode will be here from beta to 2 pi. So this area is the output voltage across the diode, and during that time our output voltage across the load, so this VO is across the load, will be equal to 0, and our current will be also equal to 0. But remember that we can also make this output voltage across the load or the current across the load through the load can be continuous, something like that. We can also extend till here depending upon the value of the inductor. So in this case we just for the understanding purpose, like I'm just keeping till beta, and then from here it is 0, and then again in the next cycle again it will current will gradually increase, and then when it reaches to 3 pi it will have the maximum, and then same trend will follow again. So from here, due to the current from the input voltage and the current from the inductor, okay, charge which is already stored in the inductor, it will try to oppose, and then the resultant will be in the decreasing. Okay, again you will have beta here, and same case we can also apply to the output voltage. From here we can draw the positive half cycle full wave, and then your output voltage is not stopping at that particular period. So instead is still I mean we still have the output voltage across the load, and until it reaches to the beta. And then after the beta, then you will again have the diode voltage during the negative half cycle. Now this is the practical aspect. And then if you want to check the performance index of this particular RL uncontrolled half wave rectifier, then we have, okay, looking at the graph here, our output voltage, since this is the rectifier, we have to calculate the DC, the average output voltage. So VO DC, or average output voltage DC, will be equal to 1 by the time period integral from 0 to t, and the input voltage, that is Vs d omega t. Now here we have the time period 1 by 2 pi is our full time period, and then from 0 the magnitude that we got, okay, we can also we can make the expression like this: from 0 to pi Vm sin omega t d omega t, plus from pi to beta, again Vm sin omega d omega t. So even if you make like this, it will be correct. Or you can also make 1 by 2 pi 0 to beta, okay, 0 to beta Vm sin omega t d omega t. Now this will be our average output DC voltage. And similarly we can also calculate the output VRMS, VO root mean square voltage. So which one will be equal to under the root of 1 by 2 pi, okay, time period from 0 to beta, and then we have V m square sin square omega t d omega t. So this one will be the expression to calculate the output RMS voltage for the RL load.